Good evening. I'm Iman Hamida, and it's my great pleasure to share my presentation at the International Conference on Intelligent Systems Design Application 2023. Today, I'll be taking you through the key aspects of my research on a bimodal autism spectrum disorder detection using fMRI images. My presentation will be divided into 5 parts: introduction, state-of-the-art, proposed method, experimental research, and conclusion. Autism spectrum disorders are complex neurological conditions with some symptoms still unknown. While traditional methods rely on psychological tests, the use of MRI images has become paramount for clinicians to diagnose ASD with precision. Diagnosing ASD is challenging because there are no definitive medical tests such as blood analysis. Therefore, the development of a computer-assisted tool for the accurate diagnosis of ASD would make it more objective and enable a faster and more efficient diagnosis. Also, the human brain comprises numerous cortical and subcortical areas, each with distinct structures and functions, making their study complex and time-consuming. Researchers use brain atlases to partition brain images into a limited number of regions of interest. They divide the brain into areas to obtain time series data to understand the correlation between different brain regions. So, based on this study, we proposed a bimodal solution that explores deep learning techniques for ASD detection using AAL and CC200 atlases from fMRI images. Now that we know what we aim to achieve, let me show you the methodologies employed to reach these objectives. A traditional AI-based methods encompass several stages of data acquisition, data pre-processing, feature extraction, and classification. In contrast to traditional methods, in deep learning-based methods, feature extraction and classification are performed intelligently within the model. In the literature, researchers are based either on a single atlas or a combination of two or more atlases. On one hand, dealing with one single atlas-based methods. In Hensfeld in 2018, the authors proposed an ASD detection method that used a stacked denoising autoencoder for pre-training to learn a deep feature representation from functional connectivity using CC200 atlas. On the other hand, multi-atlas methods consist in combining two or more atlases from fMRI scans. In this context, Wang et al. In 2020 proposed a multi-atlas deep feature representation and ensemble learning method for the ASD binary diagnosis. They calculate three functional connectivities between the time series of brain regions based on three different brain atlases. Moving on to the methodology, we'll guide you through the tools, techniques, and approaches applied in our study. The important steps involved in this process for autism detection include database preparation. This dataset have been pre-processed using the CPAC pipeline. Then we extract functional connectivity metrics, and we use autoencoders and multi-layer perceptron for classification. We divide areas for each subject based on the AAL and CC200 atlas and compute the static functional connectivity matrix by calculating the pairwise correlations between every pair of brain regions. The correlations are computed using the Pearson correlation coefficient. We focused on the upper triangular section of the correlation matrix. We excluded the main diagonal of the matrix since it represents correlations within the same region, eliminating redundant informations. During the pre-training step, the upper triangular part of the correlation matrix is flattened. The obtained vector is used as input to train the autoencoder. The encoder architecture consists of two hidden layers. The proposed method for ASD detection relies on a deep learning solution based on autoencoder. As illustrated, the proposed method is composed of two phases, a training phase and an online classification phase. In the training phase, we generate a model through an autoencoder architecture. This model will be used to extract discriminant features. As for the online classification phase, it makes use of the already generated encoder to perform the classification after fusing the two feature vectors. We trained a one-layer neural network to classify the trained features. This classifier typically consists of a single layer with sigmoid as activation function for binary classification. The inputs of the classifier are the fusion of two feature vectors obtained from two encoders separately. The model consisting of both the encoder and classifier is subsequently fine-tuned through the minimization of the binary cross entropy loss. Now we will explore the results we got from our research. We have carried out our experiments on the ABID1 dataset. The dataset was divided into 80% for training, 10% for testing, and 10% for validation. We investigate the performance of the proposed method for ASD detection through three series of experiments. The first one aims to evaluate our method using a single atlas representation. The second one validates our bimodal method that combines AAL and CC200. Finally, the third series of experiments represents a comparative evaluation with the state-of-the-art methods. In the first experiment, we evaluated the performance of our method and reported a comparative study with recent AAL-based methods. Compared to three leading methods from the recent studies, we noted that our method gave an average improvement of 1.46% in the accuracy rate over their best rate. Using CC200 brain parcellation, we obtained an average rate of 75% for the accuracy compared to well-known recent CC200 based methods from the literature. We noted that our method achieved an average improvement of 1.64% in the accuracy rate over their best rate. In the second experiment, the obtained results in terms of accuracy, sensitivity, and specificity indicate significant advantages in using two feature representations over one atlas within the proposed framework. This further demonstrates the effectiveness and distinct advantages of our proposed method in ASD identification. In the third experiment, to further validate our proposed method, we compared the achieved results with those obtained by three well-known existing works using both CC200 and AAL atlases. Our method outperforms the best accuracy rate obtained by Wong et al. With an average improvement of 1.66% and the best specificity rate obtained by New et al. With an average improvement of 10.92%, while we recorded a competitive rate for the sensitivity with New et al. This comparative evaluation proves the efficiency of our proposed generated model while using both CC200 and AAL atlases. In conclusion, autism is a complicated brain condition that affects how people think and their brain functions. We've come up with a way to detect autism using a method that combines brain imaging and two atlases. We tested our method on a dataset called ABID1, and the results show that our approach is effective in finding features that help identify autism. Our experiments also prove that our method is better than using just one atlas, giving us accurate and reliable results for autism detection. Before we conclude today's presentation, I'd like to share with you the valuable sources that have contributed our research. Thank you all for your time and attention.